In a previous lecture, we've talked about the fact that strings are very peculiar in many ways, and it's mathematics that we're doing. Throughout most of these lectures, however, I've endeavored to remove the mathematical language and instead to talk about the mathematics in terms of the pictures that sit behind it. There are some times, of course, when it's good to go back to mathematics because there's some essential points to make. The transparency I have on screen here is one reason for doing this. The old bosonic string had 25 spatial directions and 1 temporal direction, so that if we talked about the Einstein hypotenuse for such a string, it's this awful formula that you see here. Every one of these L's is a different direction. So L1 would be the first direction, the second direction, until you get all the way down to the 25th direction. Now, the other thing that had happened in string theory in our previous discussions is that we've learned that when you introduce supersymmetry, the form of the Einstein hypotenuse changes and becomes simpler. In fact, instead of having this expression go from L1 to 25, we would only need it to go from L1 to L9, not L25. Now, I have to reveal something to you that I've kept secret before now. You see, each one of these L's really is a mathematical entity that we find in string theory. So when we talk about the string being 25 dimensions, in fact, there are 25 mathematical objects that you need to talk about the string. Now, the important thing of this observation is it means that a string is really more like a stringed instrument. It's not like a single strand at all. And in fact, the old bosonic string should be thought about as kind of a guitar, some sort of a guitar or violin or whatever your favorite stringed instrument is. The old bosonic string has 25 plus 1 strands. The newer versions, the superstring, has 9 plus 1 strands attached to it. So that's the only use for this, is that we have to recognize that strings, although we talk about string like it's a single object, it's actually more like a stringed instrument, very much like a musical instrument. Now, we, in our last lecture, followed the Princeton string quartet with the construction of the heterotic string. You remember the heterotic string, it's this interesting object that combines left movers, right movers, and standing wave modes. Let's look at their pictures once more. So here we have a standing wave mode, and we'll watch it oscillate. As you can see, the red dots in this diagram do not move. The red dots are what we mean by the nodes of the vibration. On the other hand, you can see that there are these lobes that periodically disappear and reappear in the strings. The number of objects that we see there constitutes the modes of vibration. So you must distinguish the word node from mode. Basically, node means a point that's at rest. Mode means a way of vibrating. And of course, the two are connected because you can't have nodes without modes. On the other hand, in addition to the standing wave modes, we have the left moving modes. Here's a left moving mode. As you can see, it's actually this previous picture, but where the entire string rotates around. So therefore, the modes are rotating, the nodes are rotating. They have to move as a single unit. And this was a picture of the left mover. Then, of course, there are also right movers. And as you can see, the only difference is that the modes rotate in the opposite sense. In our last lecture, we also discussed how this is an echo of real physics that's been known since the 1870s. When Maxwell wrote his equations about light, it was observed that there's a property of light called polarization, which essentially tells us what's going on with the electrical field associated with a particular light ray. Now, we've also solved a puzzle in our last lecture. We said that you needed to have 496 magical charges in order to avoid the anomaly. And when Gross and Company wrote their paper on the heterotic strings, the first 2 papers at least, you will in fact not find 496 strands, because that's the important point to note. The strands that we talked about previously, which only apply to configuration space, and let's review this idea. In our world, I can move front and back. That's one independent direction. We would need 1 strand to describe that in the mathematics. We can move left to right. That's a different direction. In terms of mathematics, we would need an object to describe that. And then finally, we could move up and down. That would be a third object. Anything else we do is a combination of those three. Three strands would suffice to describe our world. But of course, we need time also. So at a minimum to describe a world, string would consist of 4 mathematical objects that we would call the string, but you can think of them as the strands of the string. It turns out that in order to get this magical 496, Gross and Company had to appeal to a very strange mathematical object called a soliton. I explained in the last lecture that there are these strange waves that can have been observed in nature, can be observed, and they have the property that these are waves that actually bounce off of each other just like real particles. Now, this is a very strange way to describe the theory because you might say, well, gee, if you have these strands for describing space, is it possible to look for this strand-like description of the charges in the theory? Now, in the original papers of Gross and Company, you will find no such signs of such a description. In one of their mathematical descriptions, they have a set of objects that are bosons. And again, I remind you, bosons are things that spin at even numbers times the spin rate of the electron. They have 16 bosonic strands in their original papers. And then they count 480 of these solitonic waves. The other thing that their original paper does is introduce 32 fermionic strands, and then they count the solitons associated with that, and they turn out to be 464. So the sums of these numbers are always adding up to the magic 496 that we need in order to get the charge conservation and the absence of the anomaly. There's something here you ought to stop me about. How can it be that these two things describe the same mathematical object? After all, I told you in our world, things like bosons are the force carriers. The particle of light is a boson, the graviton is a boson, the intermediate vector bosons even have the word boson in their name, or bosons. These are the things that carry the forces in our universe. On the other hand, the objects that the forces act upon, things like the electrons, are fermions. They all obey the Pauli exclusion principle, which is the basis for chemistry. So when I tell you this, you ought to stop me because you should say, wait a minute. Bosons and fermions are not the same objects. They're not the same kinds of objects. So how can you use them to describe a single mathematical entity? Well, the answer to that turns out to be related to some aspects of our world. And I've endeavored throughout these lectures to make sure that although we talk about the mathematics of string theory, because it is a theory of mathematics, we always try to make contact with the mathematics that is used to describe things in our world. So we're going to do this one more time. In 1911, Mercury was cooled for the first time to 452 degrees below zero. When that happens, Mercury loses all resistance to electrical currents. You can send a current through Mercury cooled to that level, and it flows with no loss of energy. That's very different from our world. Now, when that occurs, we say that the material has become a superconductor. And superconductors are one of the holy grails for our technology because you see, in ordinary wires that we use today, as you send a current through the wire, well, part of the energy of that current goes to heating the wire up. Well, that's kind of inefficient because that means that all the wires that go from the generator stations to your house are eating up energy that you don't get to use in your house. And in fact, that energy shows up in heat, and we can't do anything with that heat. So if we had a superconducting wire, it means that we could actually save energy because instead of wasting some of the energy in the wires, it would all go to households to be used. So that's why superconductors are so important. Well, superconductors, although they were first discovered in 1911, they weren't really understood until 1957. Three physicists, Bardeen, Cooper, and Schrieffer, wrote equations to explain how superconductors work. In these equations, there's a secret. In our world, charge gets transported in electricity because electrons are carrying the charge back and forth. What this mathematical work about superconductors showed was that sometimes electrons, even though they're fermions and therefore obey the Pauli exclusion principle, sometimes they can join together as if they're a single object. Now, this single object that you get out of the composite, in fact, has the properties of a boson. And this turns out to be a very important fact that allows superconductivity to work. So you can now ask the question, well, that's interesting. We take an electron and electron, join them together in some manner, and they then behave like a boson. What would happen if I took an electron and somehow magically joined it to a photon? What would that object behave like? Well, the answer turns out to be it behaves like a fermion. And in fact, there's one final thing you could ask is, well, suppose I join two photons together. What does that composite behave as? And the answer is it behaves as a boson. In fact, the statements we've just made, we can put in the form of a little multiplication table. And here it is. It says that if you take two bosons and join them together, you get something that behaves like a boson. If you take a boson and a fermion and join them together, you get something that behaves like a fermion. And if you take two fermions and join them together, you again get an object that behaves like a boson. Now, you might say, well, gee, who cares about all that? But it has important implications. But if you actually look at this table, you'll notice something else. Bosons and fermions in this little table act exactly like the numbers plus and minus 1. After all, plus 1 times plus 1 is plus 1. Well, that boson times boson is equal boson. Boson times fermion, well, that's like minus 1 times plus 1. But minus 1 times plus 1 is minus 1. Well, gee, that's fermion. And similarly, if you take two minus signs and multiply them together, you get a plus sign. But that's a boson. So the message here is that when you take joint products of these objects, you can actually figure out their behavior by simply assigning the number plus 1 for every boson, the number minus 1 for every fermion. Now, in our world, even when electrons join themselves like this together, at the end of the day, we can tell something if it's made of two bosons that are put together or two fermions that are put together. But in the world of the string, remember the string is effectively a two-dimensional world because the string has an extent and there's a time at which you look at it. So that's 2 dimensions. In the world of the string, however, it turns out that this multiplication table that we just went through is exact. In a two-dimensional world, fermions can perfectly disguise themselves as bosons. And this explains the mystery for why the original work of Gross and Company has 2 different descriptions that apparently describe the same theory. Because in one of them, what you have is that the fermions are joining together to behave as if they are bosons. Well, there's something else about this 496 that we can talk about because we haven't actually seen it. If you look at the original papers on the heterotic string, we have the strands, but we never have the strands actually equal to 496. We have the strands plus the solitons equal to 496. Now, there's a reason why this is not completely satisfactory, because if you're asking the question, what is the energy of the string? The easiest way to do that is to count the amount of energy that's carried by each strand. Since the original descriptions of the heterotic string don't have all of the objects that are necessary, remember we had to count solitons to get the charges right, that suggests that there's another formulation of this original work in 1984. Now, to get at this other formulation, once again, I'm going to turn to the example of my ladder. I know you're probably tired of it by now, but it contains so much essential physics in terms of understanding the issue of symmetry. And that's what we keep returning to, is the issue of symmetry. So here's our return to our favorite house. And there once again is our ladder laying on the ground. We can, of course, again bring ourselves close by it and grow our squares so that there's one square with an area, and we can this ladder for this one is the base of the square, but we can grow a second square downward where this ladder acts as the top of the square. And since these are both squares, the areas are the same. Now, as we tilt the ladder up, we begin to learn about invariance one more time. The area of the green is equal to the area of the brown plus the area of the blue. And this is true no matter how we orient the ladder. In fact, we can put the ladder totally against the wall, in which case it's the brown and green areas that are the same. So why do we need that in our discussion here? Well, in the context of the ladder that we just saw here, where there was something that was the same, namely the area of the green, but you could trade it back and forth between the brown and the blue. You could imagine writing some equations that show that. And I've kind of done that on this transparency. When the ladder's directly on the ground, we can say, well, gee, there's one number that's the total length of the ladder, and since none of it is up against a wall, the other number is 0. On the other hand, when we have a ladder totally vertical, then the first number that used to be the entire length of the wall is 0, and the second number, which used to be 0, is now the entire length of the ladder. So that's the mathematics. Let's look at the two pictures. Here, it's the second length. Remember, the second number talks about how much of the ladder is up against the wall. Well, how much of the ladder against the wall is exactly its length in this picture, whereas when we go all the way back to the first picture, it's actually the length along the ground that's the entire length of the ladder. That's typically the way symmetries act. So, what turns the ladder? Well, if I had a real ladder, I would have to do it. I would have to take the ladder, have it laying on the ground, lift it up until it's standing vertically against the wall. Now, there's a mathematical description of that process, and it involves describing an object whose role is to exactly take the ladder from its position on the ground to putting it up against the wall. We've met these objects before in our lectures, and they're called generators for symmetry. So we need a generator here. Now, in the heterotic string, we have our 496 generators. Those are the things that, remember, the heterotic string acts as though it's an object that has 32 different directions in which you can rotate. That's where the number 496 comes from. So we want to try to get the 496 in a more explicit way. Now, Sophus Lee, the mathematician who first invented the kinds of descriptions of these things, gave us the tools for describing rotations. And in particular, we want to use his tools to provide one more description of the heterotic string. This final description, as I mentioned earlier, will allow us to account for energy. In fact, what we're looking for is a description where there are exactly 496 strands in addition to the ones that are necessary for space. Remember, we need 9 spatial and 1 temporal strand to talk about position in space for the heterotic string. But we also want a theory where there are 496 strands that allow us to talk about the energy in a way that's completely consistent. There's another reason why we want to find this formulation. Remember when we talked about the standard model. In the standard model, there were the force carriers, and each of the force carriers is also associated with one of these generators, that is, one of these things that effectuates a rotation. So, in order to make the heterotic string appear mathematically closer to the standard model, you would actually want to find the angles that are associated with the turnings that are present in the heterotic string. Now, this was not in the original work of 1985, 1984 for the heterotic string, but, you know, in physics, we keep trying. So, how do we find this last formulation? The answer turns out to be remarkably simple. The angles that I talked to you about earlier, well, those angles, one can interpret themselves as being the missing strands that we're looking for. However, in order to write the mathematics in such a way that it's consistent, what we have to do, which is quite remarkable, is identify the angular variables that we have been speaking about with the variables that describe the 496 strands. So in particular, the way to solve our missing strand problem is to look at the right movers and not to introduce a single right mover. Imagine that there are 496 right movers in this picture. That will be the missing angles that we need. Now, what about the left moving part of the heterotic string? Well, in the left moving part, it turns out that we don't actually need any additional left movers if we compare to the original paper of Gross. All the left movers in the original paper of Gross and Company are in some sense contained in the standing ways. Now you might say, well, Jay, wait a minute, you keep saying left, right, and standing. Well, let me show you a secret to that. Perhaps you'll remember in our discussion of light, I've shown this picture before, and I said that the middle picture talks about a light way where the electrical field simply moves up and down. If we put this in motion, there it goes, electrical field vibrating up and down. Now, there's actually something quite remarkable about this picture, which is that if one were to take the right mover, so let's watch right mover, it's in the upper right-hand corner. You'll notice it rotates around in a right-handed sense. Compare that to the left mover, which rotates around in a left-handed sense. And now let's do something remarkable. Let's say, suppose we were to take the two top pictures and put them one right on top of the other. What would be the result? Well, the answer turns out to be the sum. If you take the picture in the upper left-hand corner and add it to the picture in the upper right-hand corner, you get exactly the picture in the middle. Now, how can that be? Well, let's see if we can figure this out. You see, the upper left-hand picture here has a green arrow, which is oriented exactly in the same direction as this one. If we were to put these two pictures together, this green arrow would sit right on top of that one. And therefore, if we tried to figure out the total, we could slide it along and we get a total length that's twice the length of a single arrow. Well, if you look very carefully in our middle blue line, it's actually twice the length. So now let's move the two arrows until they're pointed like this. Now you'll notice there's something interesting. The two arrows, which you can sort of think of about as two forces pushing against each other, are exactly canceling each other out because they're equally large. Well, in the middle picture, we see there's nothing there. They have canceled each other out. And now finally, rotating the arrows, continuing, we said that when they point down, the middle picture points down exactly. There's a lesson in this. The lesson is that in the heterotic string, if you look at the standing wave modes, they actually contain both left and right modes hidden within them. When you consider these 496 strands that we're talking about, the way that the picture works is as follows. You simply do a bunch of additions. You need 10 of these middle pictures because those describe the structure of the 10-dimensional world in which the heterotic string lives. You actually need also, curiously enough, 10 left movers. We can consider those left movers. And you need those for the heterotic string, but not to describe motion in space. Remember the heterotic string is supposed to spin? Well, you need the mathematical description to provide that spin. That's what these objects are. And now finally, we need these mysterious, magical 496 charges. That's what these are. So the heterotic string, if you want to think of it this way, is you take 10 times the middle picture here, you take 10 times the picture on the left, and you take 496 times the picture on the right. That's the mathematical structure of the heterotic string that we're looking for. This has the angles that look just like the angles associated with changing things in the standard model. Now you might say, wait, Professor Gates, you didn't talk about angles in the standard model, but you see I did. In our last lecture, we talked about the fact that photons are actually not directly measurable. It's the change in the photons that cause the electric and magnetic fields, and that's what we can measure in our world. If that's the case, you will also recall that I talked about that you could have two different photons, but whose changes, even though they're different, the change in each of them is the same. And so therefore, two photons that are totally different are able to produce exactly the same electric and magnetic fields. So what's the relationship between these two photons that produce the same electrical field? The answer turns out to be they're related to each other by an angular variable. And therefore, this mysterious thing that leads to charge conservation is also related to the appearance of a certain kind of angle. Now, in our world, when we talk about the forces for electromagnetism, we don't actually see any extra angles. We just see the force carriers that are related to one to another by fields that we can measure, things that are the electric and magnetic fields. This ambiguity in the relationship between the measurables and the mathematical descriptions are the things that give us these angles. So in our world, we have the gluons. There are 8 of them. That means that there are 8 angles actually associated with gluons. In our world, we have 1 photon. That means there's 1 angular variable that's associated with a photon. And finally, in our world, there are 3 force carriers associated with a weak nuclear force. Therefore, there are 3 angles. So these angular type variables actually occur in our world, but they don't refer to directions that we normally see. They refer to the fact that you're talking about the change in a photon or the change in a photon-like object. So we've actually solved a puzzle here in terms of finding this last formulation of the heterotic string where these angular-like variables appear. Now, I must admit that I'm really happy to have the opportunity to talk to you about this last formulation because you see, this last formulation is my own research. Although the heterotic string was constructed in 1984-85, this final formulation where we only found all of the angular variables associated with the string didn't occur until 1988. This was in work that I carried out with a colleague. In fact, his name is Warren Siegel. And this final formulation has all the angles. So I'm going to give you 3 scores for the heterotic string now. In the original work of Gross and Company, there's what I call formulation A. You can think of this as a score. And I've used some very sophisticated mathematics to shrink it down to this simple expression. So this is the formulation where they use what we called fermions. Those were the -1 variables that we talked about at the beginning of the talk. There's a second formulation where they use the bosons. These are all the +1s in our discussion of bound states. But neither of these formulations had the 496 angles that make the heterotic string look like our world. There's a third formulation, which is the work here, which is my own research with my colleague Warren Siegel. And it is only in this third formulation that we clearly see that the exact same mathematical structures which describe the standard model in our world are precisely present in the mathematical description of string theory. This gives us confidence that string theory is really connected with our world. One of the things that this last piece of work does that's different from the others is allow us to measure energies in a much more precise way for all of the vibrations that come from the string. In particular, there are lots of vibrations that are called spin zero vibrations that are very difficult to see in other ways of writing the thing that are very apparent in this last one. So for me, the net lesson is that you get to have fun in physics where you can make a contribution by following these very advanced topics, and you get a very great sense of satisfaction that perhaps, just perhaps, you've added a single nugget, a single strand in the tapestry that will be physics. And if we're lucky, perhaps one day, perhaps in a few hundred years maybe, this kind of mathematics will be important for constructing some useful device or process in our world. After all, that's the purpose of theoretical physics. We pursue it at one stage where it's mathematics. If we're lucky and get it right, at a final stage it becomes something important in our world. We saw this in the story of Maxwell. He predicts that electromagnetic radiation from his mathematics is light, and we get cell phones as a consequence.